Welcome to our brief video review for test number 3. So again, like in the previous two video reviews for tests, I'm just going to highlight some of the problems from the review sheet. The solutions on the review sheet are pretty comprehensive, so I think you will be able to follow those fairly easily without me, without comments from me. But in any event, I'm just going to mention a few of them from the review sheet. Now, keep in mind for test number 3, like always, right? You can bring your calculator, of course. Just keeping in mind that you're going to have to show your work, right, on the test for full credit, right, if you have a problem that requires work. And most of these problems, of course, are fairly computationally intense, right? So you will have work to show. And then, of course, you can bring your survival card, right? So so there may be some things, right, that you want to put on your survival card to bring to test number 3. And that's going to be the same setup for the final as well, right? You can have your calculator and also your survival card. Now, as I mentioned in class, we're not going to include all of the problems from this sample test on test number 3. Some of those we're going to defer to the final exam. So that will include integration with polar coordinates, right? Double integration with polar coordinates and triple integration. So those are the last 4 problems, I think, from this review sheet. So we will stop for test number 3. We will stop at problem number 10, right, on the review sheet. So you really don't have to prepare past problem number 10 for the test number 3. But then those last few problems from the review sheet might be included on the problems like those might be included on the final exam. Okay, so let's get started here so we don't make the video too long. So let's look first down here to problem number 2. So problem number 2, there are several parts to this, but in all of these problems, we are going to be using the second partial derivative test, right, to locate maxima, relative maxima and relative minima on the surface of a function of 2 variables, right? And so this is an important skill that, of course, is going to be covered on the test. So that's something you want to pay particular attention to, because I think those problems are fairly routine, because we're just applying this second partial derivative test. Sometimes the partials may be hard to compute, but the process is fairly rote, right? Because we're applying this second partial derivative test. So this is probably something that you can score really well on if you're prepared on test number 3. And so that means on your survival card, you might want to write down, right, at least an abbreviated version of the second partial derivative test. I copied kind of a short version from the notes, cut a short version from the notes that I pasted here onto this review. It's on the next page, so I'll show it to you in just a second. Let's start though with problem number 2, right? So this is just going to be part A, right, from problem number 2. So this is just going to be a very standard application of the second partial derivative test. So there we have, our function of 2 variables, right? So we can plot that, and that's going to be some sort of quadratic surface, I think, if we plot that, and we're just looking for, right, if we have any minima, right, local minima or local maxima, right, or possibly saddle points, remember, on the surface there of the graph of this 2 variable function. So, of course, to apply the second partial derivative test, you're going to have to calculate all of the partial derivatives. So that's what I've done here. That's what you're asked to do, right, at the first part of the problem, because you're going to need these anyway, correct? So there's the first partial derivatives, right, with respect to x and y, and then you can use those to calculate the second partial derivatives, right, the the second partial derivative with respect to x, the second partial derivative with respect to y, and then the mixed partial derivative, right? First x, then y, or you could do first y, then x. And those come up, of course, in the second partial derivative test. So I think we've covered calculating partial derivatives on the second test, so I don't need to review that. I think you can do that probably pretty easily, right? Okay, now how do we apply those partial derivatives, right? So in that second partial derivatives test to find relative minima and relative maxima. Well, of course, first thing you're going to do is find the critical points, right? Okay, so the critical points are the points that make both the partial derivative with respect to x and the partial derivative with respect to y zero simultaneously, right? So you're going to set those two first partial derivatives to zero, and that will give you a system of equations in two variables. And then you want to solve that system of equations in two variables. It turns out to be an easy system in this case, though, to solve, because when you set the partial with respect to x to zero, you just get an equation involving x. And so that's easy to solve just for x, right? And then when you set the partial derivative with respect to y, right, to zero, that just gives you an equation involving y with no x's. And so you can just easily solve that equation for y. So you have a critical point at x equal 4 and y equals -1. By the way, the corresponding point on the graph, right? The point on the surface that corresponds to this this critical point would be, you calculate that, right, just by taking x equal 4 and y equal -1 and plugging it back into the formula for the function, right? And that gives you the matching z value here, which turns out to be 9, okay? So the actual coordinates of the critical point on the surface will be 4, -1, and 9. And what we want to do, of course, is check to see if that is possibly a local maximum or possibly a local minimum, and that's where the second partial derivative test, right, comes into play. So there's a little abbreviated version there of the second partial derivative test, right? So remember, in the second partial derivative test, you need to compute this value d, correct? So there's the formula for d, and that means you take the product of the second partial derivatives, right? The second partial derivative with respect to x, second partial derivative with respect to y, evaluated at your critical point, x equal 4, y equal -1. Take that product and then subtract off the square of the mixed partial derivative, right? Also evaluated at your critical point, in this case, x equal 4 and y equals -1, right? And then you're going to use that value in this recipe, correct, to determine if you have a relative maximum or a relative minimum, or possibly a saddle point, or maybe the test is inconclusive. Sometimes the test fails if this value for d turns out to be 0. Okay, so let's see what we get for this particular critical point, right? When you evaluate the second partial derivative with respect to x at your critical point, you get -2, which is less than 0, right? So we want to keep that in mind. There's the second partial derivative with respect to y evaluated at our critical point, we get -8. And then when we take the mixed partial derivative, first x, then y, or you could use first y, then x. Either, remember, those two things are going to be equal, so it really doesn't matter which one you use. Evaluated at your critical point, in this case, that turns out to be 0. Now we compute our value for d, right? So we take the product of the second partial derivatives, right, minus the square of the mixed partial derivative, again evaluated at our critical point. In this case, we get 16, which is positive. So we look in our little chart here, right, and we notice, let's see, d is positive, correct? D is positive, but the partial derivative with respect to x the second partial derivative with respect to x is negative because we got -2 here, right? And so that means that our critical point is a relative maximum. So that's why I filled in this box, right? We have a relative maximum at our critical point for -1 and 9. Since that's the only critical point, then that means we don't have any relative minimum, right? Because there's no possibility for a minimum, or we don't have a saddle point either, right? So again, if you can just remember this test, right, and and you're not getting sloppy at computing your partial derivatives, then it's pretty easy, right, to apply the test and get the right answer here. Let's try another one a little bit further down the list here. So see which one I circled. I think it's the last one, which is D. All right, so there's our function of two variables, x minus 2 squared, y plus 3 squared. So again, looking for relative maxima or relative minima, or maybe saddle points. So we're going to compute our partial derivatives. So be careful that you compute the partial derivatives carefully. There are the first partial derivatives computed, and then here are the second partial derivatives computed and the mixed second partial derivatives computed. And so we take our first partial derivative with respect to x, set that to 0. First partial derivative with respect to y, set that to 0. Solve this system of equations. Again, it turns out to be, again, easy to solve this system of equations because both of your equations end up just involving a single variable, right? And so you can just solve this equation for x, you get x equals 2. Just solve this equation for y, you get y equal -3. So you know you have a critical point at x equal 2, y equal -3. When you evaluate that in the original function, you get an output there, a z value of 0. And so there's our actual point on our surface. The actual critical point on the surface is 2 minus 3 and then 0. So actually, this critical point sits on the xy plane, right? Because the z value is 0. And now we're going to apply our second partial derivative test, right? So we want to pay attention, right, to especially to the partial derivative, right? Second partial derivative with respect to x. So when we evaluate that at our critical point, we get 2, which is positive. Here's the value that we get for the second partial derivative with respect to y. That's -2. And here's the mixed partial derivative, second partial derivative, also at the critical point. That turns out to be 0. So when you plug those values in and compute d for your second partial derivative test, you get, of course, 2 times the -2 minus the 0 squared, and that turns out to be -4, which is less than 0. So what does that mean then in our second partial derivative test when the d is negative? Well, we don't even care about the second partial derivative with respect to x when d is negative, right? When d is negative, that means you have a saddle point. So our critical point is this critical point is a saddle point. So it's neither it is a critical point, but it's neither a local maximum nor a local minimum. All right. Now, let's look at kind of an applied problem also involving the second partial derivative test. So this is an application in geometry. And so what we're asked to find is I wish I had a picture of this situation, but it's not that easy to draw in 3 dimensions, of course. So we want to find the minimum distance from this point, 214, to this surface. That surface is a plane, of course, right? That's the equation for a plane. So we want to find what's the minimum distance from this point plane. We should check to make sure that this point is not on the plane, right? Okay, because if the point is actually on the plane, this plane described by this equation, then of course the minimum distance is 0, and so we don't have any work to do. But I think if you plug in actually, right, the coordinates of this point into the equation, you get 4 equals what? 4 minus 1 minus, sorry, 4 minus 2 minus 1, and because x is 2 and y is 1, right, at this point. And so that's not true, correct? That is not a true equation. So that means this point does not satisfy the equation. That means this point is not on this plane, correct? Oh, great. So we do have an actual distance, right, from this point to this plane. So how can we find that? Well, what we're going to do, of course, is actually compute the distance from this point, right, to the plane. Okay, so the actual distance from this point to a point on the plane, and then we'll try to find out, well, which point on the plane gives us the minimum distance to this point. So do you understand the logic there? Here is an arbitrary point. These are the coordinates for an arbitrary point on this plane. So if it's an arbitrary point on the plane, you can have any x coordinate, any y coordinate, but of course the z coordinate must satisfy this equation, right? So you know all your points on this plane, all those points, their coordinates look like this, right? And so you can now compute the distance from an arbitrary point on the plane to the given point, 214. And we'll try then to find, well, what choices for x and y would give us a minimum distance, right, to that given point, 214. So that's the logic that we're going to use here, right? So actually now, we just use the distance formula, right, to compute the distance from the arbitrary point on the plane to our given point, 214. So I just filled in the coordinates for this point and the coordinate for our given point, right? The coordinates for our given point into the distance formula. So you know the distance formula, right? It's distance of the x, the distance between the x coordinate squared, right? The difference between the x coordinate squared, the difference between the y coordinate squared, plus the difference between the z coordinate squared. Be careful with the signs there, and then you take the square root of that to compute the actual distance. But to make calculations easier, this square root, of course, is a little bit clumsy. So we're going to square the distance. So instead of just thinking of the distance between this arbitrary point and our given point 214, we're going to actually use the square of the distance between our point on the plane, our arbitrary point on the plane, and the given point. So we don't have to deal with a square root. So this is actually the function that I'm going to try to minimize, right? I want to see if I can find a minimum value, right, for this particular distance squared. And a minimum value for the distance squared will also correspond to a minimum value for the distance itself, right? Not squared. All right, so just think of this, the d squared here, as a function of two variables. And let's see if we can discover if it has a minimum, right? All right, so, well, how do we do that? Well, we're just going to use our second partial derivative test. So we're going to calculate the partial derivatives, right? The first partial derivatives and the second partial derivatives. Look for a critical point, correct, right? And then hopefully check to see if that critical point represents a minimum. You'll of course, you can see already in the solution that it does, but let's see how we arrived at the fact that well, first at that critical point, right? And then at the fact that critical point corresponds to a minimum. All right, so remember, take your first partial derivative. So here they are calculated. Partial derivative with respect to x, partial derivative with respect to y. Here's the partial with respect to x simplified a little bit. It's just 4x plus 2y minus 4. Set that to 0, right? And then take your partial derivative with respect to y. So that turns out to be 4y plus 2x minus 2 equals 0. And solve that, then solve, right, that system of equations. Now, that system of equations is a little bit tougher to solve than the ones in problem number 2, because both of these equations involve both variables x and y. So I'm going to have to do a little bit of algebra here to actually solve these equations simultaneously. I think what I did was I took that first equation and moved the minus 4 over to the right-hand side. So I got 4x plus 2y equals 4. And then took the second equation and moved the negative 2 over to the right-hand side. So I got 2x plus 4y equals 2. And then I noticed, well, if I take the second equation and multiply both sides by minus 2, that would give me minus 4x minus 8y equal minus 4, right? See, I took the second equation and multiplied it by minus 2. Now, the reason I multiplied that second equation by minus 2 is now I'm going to add this equation and this equation together. And the reason I want to do that is the x terms will drop out, you see, when I add now this equation and this equation together. So you end up getting, well, 4x minus 4x is 0, so no x's, right? 2y minus 8y is minus 6y, and then 4 minus 4 is also 0. And see, now I have an equation with just y in it, and now I can easily solve that for y. In fact, it's trivial, right? We get that y is equal to 0. Now that I know 0 is the coordinate of is the y coordinate of my critical point. Now let's take the 0 and plug it back into one of the two original equations, right, that came from the first derivatives. I used the first one, I think. So I plugged 0 in for y here. Of course, that zeroes out this term, so you just get 4x is equal to 4, and then it's easy to solve for x, right? You just get x equal 1. Oh, so I know the x and y coordinates of my critical point are 1 and 0. And now just plug 1 and 0 into your function. Remember, that's the distance squared function, and you end up getting z is equal to 3. So I think I might have I have a critical point. I'm hoping it's a minimum, right? I have a critical point on the distance squared function at 1, 0, and 3. That's now where we're going to apply the second partial derivative test, right? So here I've computed my second partial derivatives there with respect to x. That turns out to be the constant 4, nicely, which is positive. And there's my mixed partial derivative, x and y. That turns out to be the constant 2. Okay. Is that the constant 2, or maybe that's after I have evaluated at 1 and 0? Don't forget, you have to evaluate your second partial derivatives at your critical point, right? At any rate, you get 2 for the mixed partial derivative, and then just compute your d value, right? So this is fxx times fyy. That also turned out to be 4, by the way, and minus my mixed partial derivative, which is 2 squared. So that arithmetic turns out to be 12, which is positive. So the second partial derivative with respect to x is positive. The d value is also positive. That indicates, according to the second partial derivative test, that I have a minimum, just exactly like I wanted at this critical point. Oh, great. So I think We have a minimum there at 1 and 0, right? Okay. And so now, what is the minimum distance? Well, you know the distance squared at this critical point is 3, because we calculated that a moment ago, right? And so that means that the minimum distance is the square root of 3. Ah, there it is. Okay. So the shortest distance from our given point to this plane turns out to be the square root of 3. All right, so there's a little geometric application that's a little bit more involved, but once you set up your function right, then still easy to find the critical point and to discover using the second partial derivatives test, right, that is a minimum. What's a little bit more complicated is solving this system of equations, right, that you get when you set your first partial derivatives to 0. So be aware you may have to do that, right, on the test. So try to recall, right, how to solve these 2x2 systems of equations, right, that involve two variables, x and y. All right, I'm going to pause here for a moment, and then we'll come back and look at the next problem, or another problem here on the review. Okay, let's resume. So now we're going to switch to integration. So maybe a little bit tougher, right? Because integration is always a little bit worse, I think, than differentiation. But not a difficult problem, at least to start with here, maybe. Okay. So here we're just, we don't have to set up this double integral. We just want to evaluate this double integral. All right. So we can think about, drawing this region of integration and so forth, and the region of integration that's described by these limits of integration, right? But that's not really necessary. We really don't have to geometrically understand in this case what we're doing in this problem, right? We just want to carry out the computations correct. So first we're integrating with respect to x, right? With these limits of integration, and then integrating with respect to y with these limits of integration. All right, so let's start here. So since we're integrating with respect to x, then and sine squared y, right, doesn't involve the variable x, then sine squared y is just a constant, right, when we're integrating with respect to x. So it's very easy to integrate this integrand with respect to x, right? You're just going to treat that as a coefficient for just the variable x, right? So this antiderivative of sine squared y with respect to x is just x times sine squared y, and then we want to evaluate that from 0 to cosine of y, right? So we're going to plug in cosine of y for x, and then we're also going to plug in 0 for x and take the difference, of course. Well, so nice to have 0 as a limit of integration as usual, right? Because when you plug 0 in for x, you just get 0. So all you really get, right, from this inner integral is just cosine of y substituted for x, right, times sine squared of y. And so now we want to integrate that, right, from 0 to pi. All right, now this, of course, antiderivative is a little bit harder to discover, right? So how do we integrate sine squared y times cosine of y? I think the thing to notice here is that we want to use the power rule. We would like to we want to think of the sine squared y, of course, as, which it is, as sine y squared, right? And then somehow be able to apply the anti-power rule to do the integration, correct? Of course, the anti-power rule means we would add 1 to the exponent and divide by that new exponent. Unfortunately, this is not just the variable squared, right? We have this expression squared. So to simplify this antiderivative, let's do a, I'm sorry, to simplify this integrand, let's do a substitution. So what we're going to do is let u be sine of y, right? So I hope you're not having difficulty doing integration by substitution. We've practiced it a few times in class, but I know it always remains sometimes a little bit confusing. So I'm going to substitute u for sine of y. And the advantage to that is it simplifies the integrand, right? I will just have here, instead of sine of y squared, I'll just have u squared, right? Just a variable squared, and then I can integrate that using the power rule. But of course, before we before before we actually integrate, right, I have to make sure that I dealt with changing the variable of integration correct. So from y to u. So of course, the way you do that here is in your substitution, u equals sine y. Go ahead and compute the derivative u with respect to y, right? In other words, du dy. And that turns out to be, of course, cosine of y. So easy derivative to compute, and then solve this for dy so that we can substitute for dy. And I think we get that dy, right, is equal to du over cosine of y. So this is what you're going to substitute for y, right? This is what you're going to substitute for dy. So that turns out to be a really convenient substitution because you get what? Cosine of y times, remember, we're going to let u be sine of y. So this is just u squared times, and then dy is du over cosine of y, right? And now, fortunately, the cosines divide out. So we do end up with an integrand that just involves the variable u, correct? So we just have this very simple integrand u squared du. Technically, I'm supposed to change my limits of integration here also, right? Because these limits of integration apply to y and not to u, but that's okay because remember, we're going to undo the substitution here shortly. So let's not bother with changing the limits of integration. So how do we integrate? How do we integrate there? U squared, well, that's just the anti-power rule. So that's going to be u cubed divided by 3, right? Add 1 to the exponent. And then we're evaluating that from 0 to pi. But now let's undo our substitution so that these limits of integration become valid again, right? And remember, u is sine of y, right? So we have here sine cubed y over 3 evaluated from now evaluated from 0 to pi. That's what I have written here, right? As our as the value of our definite integral, correct? And now when you evaluate that, apparently from 0 to pi, you just get nicely there 0. So this this double integral, this definite double integral, just turns out to be 0. Okay. Let's try one that maybe doesn't require substitution. So I'm looking now at 6b. All right, now here's the problem in 6b. It's an application of double integrals. It's not just a straightforward double integral. What we want to find using a double integral is the area between these two curves. So this is really a calculus, well, actually between these 4 curves, right? This is really a calculus 1 problem. We're just computing an area in the xy plane, but we're going to use our knowledge of double integration actually to compute this area. So look, you really need to draw a picture of the area to understand how to set up the double integral properly, right? So I've sketched here very briefly, very roughly, and your sketch can be equally rough. Just make sure it's something that's useful to you. I've sketched here this region in the plane. So of course, x equal y or y equal x, that's really easy to draw that, right? A line, right? That's just a 45-degree line here, right? So there's x equal y, right? Y equals 0, of course, is just the x-axis. So here's y equals 0, and then y equal 2 is just a horizontal line, right? So there's y equal 2. I didn't draw that horizontal line very horizontally, but that's supposed to be a horizontal line here across, right? And now, so the only other part of the region that we need to draw is this curve, x equal y squared. So you need to think about what that curve is going to look like. It's not y equal x squared plus 5, it's x equal y squared plus 5. So you're going to get a parabola here, right? Because this is a quadratic curve because the y is squared. But this parabola is going to, instead of opening up, this parabola is going to open to the right. So it may help you to plot a couple of points on the parabola. You might try to find the x-intercept by setting y to 0, right? So when you set y to 0, you get x is equal to 5. So this parabola is going to cross the x-axis down there at 5. You may also want to try plugging in y equals 2, because you do want to know, right, where this horizontal line and this curve cross each other, right? And remember, this horizontal line is y equal 2. So if you plug 2 in for y, you get a matching I wrote the coordinates backwards there. You get a matching x value, right, of 9. So this is really the point 9 comma this is really the point 9 comma 2, right? Okay. So that will, and so you're going to have a symmetric point here also below the you're going to have a symmetric point here also below the x-axis. And so if you connect those points, you get this nice parabola. So here is our this little piece right in here, right? That is the region that we're trying to compute that's the region that we're trying to compute the area of. Now, look, it's important to notice that this is a horizontally, not vertically, but a horizontally simple region, because it is just the region between two curves, one curve on the left and one curve on the right. Okay. It's between, on the left, the curve x equal y or y equal x, and then the curve on the right here is, x equal y squared plus 5, right? So that is a horizontally simple region, right? It's not vertically simple because it is not the area between one curve on top and one curve on bottom. Notice at the top of this region, there are two curves that define the upper boundary for this region, right? This line and this 45-degree line and this horizontal line, not just a single curve. And then on the bottom, there's also two curves that define the region, right? The x-axis, and then a little bit further to the right here, this parabola, correct? So it's not vertically simple, it's horizontally simple. That means then that the convenient order of integration is going to be first with respect to x and then with respect to y, right? Fix a y value first, figure out what the what the limits for x are going to be when you fix that y value. But because this is a horizontally simple region, when you fix the y value, you just have this curve on the left, right, and this curve on the right as the limits for x. And then you can consider and then integrate with respect to y, and then consider the boundary for the y values. since we're computing the area of a region, right? Remember, we're going to use an integrand of 1, so I didn't even copy it in there, but that integrand is understood to be 1. So I'm going to integrate with respect to x first, and then with respect to y. What are the limits here in this region for x? You're starting at this curve, right? Which is x equals y. So you're starting at y on the left, and you're going over to this curve on the right. What's that curve? That's x equals y squared plus 5. So there are the limits of integration for x. And then for y, let's see, what are we doing? For y, we're starting at 0, and we're going up to 2, right, on the y-axis. Starting at 0, right? With the x-axis, and then going up to this horizontal line, which is y equal to on top, right? So the limits of integration for y are from 0 to 2. So there is the double integral that we can compute to find that area. Now the rest of this is pretty straightforward, okay? Because your integrand is 1. So remember, when you integrate 1 with respect to x, you're just going to get x, right? This integral, this inner integral is just going to get, I have room to write it in here, but this inner antiderivative is just going to be x, plain x, because you're just integrating the 1, and you substitute the y squared plus 5 and subtract off what you get when you substitute the y. So you just get y squared plus 5 minus y for that inner integral, right? And now you just evaluate that from 0 to 2. And there you can integrate just using the anti-power rule. So that's what I've done here. I've just integrated using the anti-power rule and evaluated from 0 to 2. If I did my arithmetic correct, we come out with an area of 32 thirds. Okay, so see, drawing the region of integration, really crucial here, I think, to help you set up the double integral. So I'm always encouraging to draw regions of integration to help you understand how to set up your double integrals, or if the case may be, triple integrals as well. I did not do that in the answer key for 6a to find the area between these two functions. I think this is a vertically simple region. So since it's vertically simple, notice my order of integration is different. I went dy dx, but you can draw a picture of these two curves. These are parabolas as well, right? And we want to find the area between these two parabolas, draw a picture of those two parabolas, right? And also you want to figure out where those two parabolas intersect. I think I did that by setting the two formulas equal to each other, right? And finding these 2 points of intersection. So draw a picture of these two parabolas, and then, right, so you can see why x equals 0 and x equals 4, right, are where those two parabolas intersect. So that give you a better idea of, how to set up this double integral. Okay. All right, so let me pause again. We're going to continue with double integration, though, on now in problem 7b, but we'll come back to that after the pause. Okay, let's look at the next problem here, which we're going to do is 7b. So here we don't actually have any integration to carry out, so that's nice. We're given this double integral. It looks like this is an integral that would be used to compute the area of a region in the xy plane, right? Because the integrand is understood there to be 1. All we want to do is draw a picture here of this region of integration implied by the limits of integration, and then looking at the picture, see if we can change the order of integration. So our original order here is dx dy, and that sort of implies that this region is horizontally simple, right? Okay, so it's just the area between two curves, just two curves, right? One curve on the left and one curve on the right. Let's see if that's true. So let's see. we're going from 0 here, an x value of 0. So that implies the y-axis, right, is going to be one boundary, the left-hand boundary for our region. And then this curve, x equals 1 minus y squared, that apparently is going to be the right boundary for our region. Well, of course, the x equals 0, as I just mentioned, that's the y-axis. So nothing really to graph there. Let's see if we can graph x equals 1 minus y squared. So again, just probably from your knowledge of algebra, right? Because that y squared term, you know, this is going to be some sort of parabola. Since the coefficient on the y squared is negative, that means the parabola is opening. It's going to be a horizontal parabola, but since this coefficient is negative, that means the parabola is going to open to the left instead of to the right. If this were a positive coefficient, the parabola opening to the right. So we have a parabola that's opening to the left, like you see here. That is the graph of 1 minus x equal 1 minus y squared. You can plot a few points on that curve by, you know, maybe looking at the x-intercept, set y to 0. So if you set y to 0, x is 1. So the x-intercept there is going to be 1. You might try finding the y-intercepts, right, by setting x to 0. If you set x to 0 and solve, you get that y is going to be plus or minus 1, right? So it's going to cross the y-axis at plus or minus 1. So it's pretty easy there then to just connect those dots with the parabola, right? So there's the parabola that forms the right-hand side of this region. And that's really all you have to graph, right? Here. So let's see now. Of course, the boundaries on the y are going to be y equal minus 1 to y equal positive 1 is implied by this picture, right? Let's see if we can change the limits of integration from I'm sorry, the order of integration from dx dy to dy dx. So that means we have to also be able to treat this region as a vertically simple region as well, which means we want it to be just the area between two curves, one curve on top and one curve on bottom. So what we have to do is sort of split this parabola into two parts, right? This curve on the top and this curve on the bottom. So if you take x equal 1 minus y squared and solve that for y, write that as a function of x instead of as a function of y, well, you get y is going to be plus or minus the square root of 1 minus x. So that means this top curve is, its formula is y equal positive square root of 1 minus x, and this bottom curve is y equal minus the square root of 1 minus x. So if we think of that as a vertically simple region, then our limits of integration on y, right, are pretty obvious, right? You're going from y equal the bottom curve, which is square root of 1 minus x, up to y equal the top curve, which is the square root of positive square root of 1 minus x. And then x, of course, is just going to be running 0 to 1. So with a little bit of algebra there, we can easily switch the order of integration. Let's try now a part of this next problem, problem number 8. So here we're actually asked to carry out an integration, right? Actually do the computation. It says complete the double integral to integrate the given function over the indicated region. So we're going to be, instead of the picture of the region drawn for us, we're going to be given the region described in words, and we're going to have to draw the picture of it. And then we're going to have to figure out what's the most convenient order of integration, and then what are the limits, right, that we need to use for that order of integration to integrate this function, 6x squared, over that given region. All right, so in 8b, the region that's described there is bounded by y equals 0. So that's the x-axis. That's pretty easy, right? And then also, apparently, on the right-hand side, this vertical line, x equals 1. But then also this curve, so here's x equals 1, right? So we're bounded on the right by that. But then also the curve y equals square root of x. So here's a graph of y equals square root of x. Of course, it crosses the origin because when x is 0, y is also 0. So it crosses the origin, right? And then you do get this is square root of x, right? It's not a straight line. So you get some curvature here when you graph y equals square root of x. But my drawing here makes it look like a straight line, but it's really not, right? Y equals square root of x is not a straight line. It does pass through, though, the point 1, 1, right? That's where, of course, this vertical line x equal 1 and this square root of x, that's where they intersect at the point 1, 1, because when x is 1, y is also 1, right? The square root of 1 is 1. So that point is kind of important, well, semi-important to know, right? So this is it's easy to see that this is a vertically simple region, right? But this is also a horizontally simple region. So we actually could have done the order of integration either way, okay? Either dy dx or dx dy. But I think first I was looking at it as a vertically simple region of integration. So I used the order dy dx, right? It's vertically simple because it's just the area between this curve on top and then the x-axis on bottom, right? Well, okay, so what are our limits on y? Y starts at, so if we're going to use dy dx as the order of integration, let's see, x starts at, y starts at 0, right? And goes up to this curve, which is y equal to square root of x. So the limits of integration with respect to y are 0 to square root of x. And then with respect to x, right, pretty simple. You're just going from 0 to 1, right, on the x-axis. So the limits of integration with respect to x are just 0 to 1. And now we just compute that double integral. Well, I don't think you really need any help with carrying out this integration. Notice it's easy because 6x squared is a constant with respect to y. So when you integrate 6x squared with respect to y, you just get 6x squared times y, right? And then substitute the limits of integration, end up with something like 6 times x to the 5/2 power. Going to convert that square root to a 1/2 power. So we get 6x times 6x to the 5/2 power. And then when you integrate that with respect to x, just apply the power rule again, right? So add 1 to the 5/2 and divide by 5/2 plus 1, which is 7/2. So you get 6 times x to the 7/2 power divided by 7/2. And then just have to substitute the limits of integration. Well, those are very easy limits of integration, right? To evaluate the 7/2 power is no difficulty when you're just substituting 1 or 0 for x. So I think you come up with, if I did that calculation correctly, 12 sevens. Okay, well, we're getting close here. Let's see what left we have. And now we get to the sort of the meatiest problem here, right? Which is we want to calculate the volume using a here, right? Using a double integral. Okay, so the real key here, of course, is just discovering, I don't know if I drew a picture of it. The real key here, of course, is just trying to write down your real key here, right? Is just trying to write down your limits of integration for your region, right, in the XY plane, because this volume that's shown here is just the volume beneath this surface, which is just this plane, z equal 2 minus x minus y, right? If you solve this planar equation for z, you get z equal 2x. You get z equal 2 minus x minus y, right? So the volume beneath this plane down to this region, this triangular region in the XY plane. So we're thinking of this as being our function, right, of two variables, z or f of xy, right, equals 2 minus x minus y, and we're just trying to integrate that function right above this particular region. So I didn't redraw a picture of this region in the XY plane. It's very easy to do that though, right? So if you just scribble here quickly a picture of the XY plane, you just get this very easy line, right, that goes through 2 on the x-axis and also goes through 2 on the y-axis, right? And the equation for that line you can get pretty easily just by computing the trace of this plane, right, in the XY plane, the trace of this surface in the XY plane, and you get that just by setting the z, right, the surface to 0. So you get 0 is 2 minus x minus y, and when you solve that for y, you get y is minus x plus 2, or you can also write that as 2 minus x. So this is the line y equals 2 minus x. So here is our region of integration. So we just set up the boundaries on our double integral, right, to describe this region of integration, and then, right, we're just integrating this function, right, over that particular region. So this region of integration is both vertically simple, because it's the area between, right, two curves, one curve on the bottom and one curve on the top, this line on the top. It's also, however, horizontally simple as well, because again, it's the area between one curve on the left and this line, one curve on the right. So you can really use either order of integration, dx dy or dy dx. I think I thought of this as a vertically simple region, so I used dy dx, but it would be just as easy to set up dx dy. So if we think of this as a vertically simple region, fix a value for x, right? And think of how does y run for that fixed value of x. What's the domain of y for that fixed value of x? Y starts here at 0, of course, on the bottom, because the x-axis is our boundary on the bottom, right, and goes up to this curve on the top, whose formula is y equals 2 minus x, right, that we just discovered. So if we use dy dx as our order of integration, there is our inner limits of integration. And then what about our outer limits of integration? X is running from 0 up to, well, of course, 2 on the x-axis, right? So our outer limits of integration are 0 to 2. And I think now I don't need to step through all of the steps of this integration. This is fairly straightforward integration, right? Okay, I think the only rule for integration you're going to have to use here is our favorite anti-power rule, right? And the the arithmetic, I think, is kind of messy, but you can work your way through the arithmetic. We eventually come up here with a final value for that definite integral of 4. So apparently this volume is 4/3. Is that believable? I'm not sure. Okay, so somehow that volume looks a little bigger to me than thirds, but who knows? Okay, this is what we got. Is 4/3. Remember, this is cubic units, right? Because this is a volume. So double check my arithmetic and see if my integration in my arithmetic and see if we really do get a value there of 4/3. We're setting it up properly though, so just a matter if I went through these steps correctly. All right, one last one to look at. We're not going to really dwell on this last one. It's just an applied problem. Just want to remind you, I mentioned this in class, that you also need to be able to find the average value of a function of two variables over a particular region. And you do that by computing the volume of that function over the region and then divide it by the area of the region of integration. So here's that problem in an applied setting. So we're told that the temperature of on a particular location on a surface of some material, it's metal, a rectangular metal plate, that temperature at a particular location xy on that surface, you can impose a Cartesian coordinate system on that flat metal plate, right? So that allows you to locate points on that metal plate using your familiar rectangular coordinates, right? But the temperature at a particular location on that plate then is given by this formula. So T there is temperature. And we want to know what's the average temperature on that plate. Okay, so the temperature is varying from left to right and top to bottom on the plate. So different locations have different temperatures. I want to know what's the average temperature over the entire plate. So by the way, it tells you that the way we've superimposed the coordinate system, our rectangular coordinate system on this plate, the x is going to vary from 0 to 3, and the y is going to vary from 0 to 5. Okay. All right. So how do you calculate this average temperature? Well, that's just an average value computation. So you just integrate the two variable function, right, over this region and then divide by the area of the region. And the area of the region is easy to calculate since it's a rectangular region. The area is just going to be length times width, right? So that's just going to be 3 times 5, which is 15. And then when you integrate this temperature function, right, over that region, that double integral is also easy to calculate because the limits of integration are easy to set up, right? If you go in the order dy dx, y is running from 0 to 5, right? So our inner limits of integration would be 0 to 5, and x is running from 0 to 3, so our outer limits of integration would be 0 to 3. So you just integrate this function of two variables over that region. That's a pretty simple double integral to calculate. You just have to use the anti-power rule to compute any derivatives here. And you end up with 410 as being the value of that double integral. And then divide that by the area of the region, which is 15. So you get 82/3 as being the average temperature of that metal plate. Okay, so well, there are the problems that I wanted to highlight. Remember, the remaining problems, 11 through 14, are about polar integrals and triple integrals. I think they're fairly easy to understand the solutions that I've given, because I think I included enough detail that you can understand the solutions. But in any event, we will save those types of problems for the final exam. So you can use 11 through 14 when you're preparing for the final exam, which is on December the 12th. All right, guys, so I'm going to see you on Monday, December 5th to take the test. Good luck with that. Make sure you've got your survival card prepared, right? Before the test. So see you on Monday.